Alright folks, here we go, lecture for Chapter 8. I'm experimenting with different video delivery techniques, and right now I'm using my husband's GoPro camera, which has a fisheye lens, which is why this video looks a little trippy and distorted. But I think everything is in focus better than when I tried to just film it on using my computer webcam. And I want you to be able to see the slides, and also I like being able to write on the board as opposed to trying to write using my computer cursor. So we're going to give this a shot. Again, this is going to be a long lecture, Chapter 8. Normally I would take 2 classes to go through this material, but since I'm doing this on video, I thought it'd be easier to just get through the whole chapter in one lecture, and you can watch it in pieces if you would like. And maybe if requested, I can post sort of a review, like a Chapter 8 review type of lecture where I just highlight and hit on some of the major points. So Chapter 8 is all about acids and bases. And so we're going to go through and talk about what it means to be an acid or a base, what are the definitions of acids and bases. Then we're going to practice identifying acids and bases in chemical reactions and learning how to write chemical reactions with acids and bases. We're going to talk about chemical equilibrium. We've talked a little bit about equilibrium arrows when we were talking about solubility and weak electrolytes, but we're going to come back to it here. And then we're going to talk about pH, which is how you measure the acidity of an acid or a base. And then, of course, at the end of the chapter, we always bring it back around to why acid and base chemistry is biologically relevant and relevant in a physiological system. Excuse me. So some sort of common layman's characteristics for acids and bases are that acids tend to be sour tasting. Most foods, a lot of foods are acidic. In fact, there's very few foods, I don't think there's any foods that are basic, unless you count like baking soda as a food. Milk is probably the most basic food, and it's a pH of 6, which is actually still acidic. So anything under pH 7, and we'll get to that, is acidic. So some particularly acidic foods, lemons, pickles, sodas, all contain a lot of acid, citric acid, and it has that sour sort of taste to it. Bases, their sort of standard characteristics are that they're very slippery, and a lot of household cleaning products contain bases in them that help clean off grease. Liquid plumber is straight up strong base. Soap is actually slightly basic. The process of making soap involves using a base. So most soaps are actually a little bit on the basic side, some more than others. So what are the chemistry definitions of acids and bases? Well, there's 2 different people, 2 different scientists, I suppose, or groups of scientists who defined acids and bases differently. So there's the Arrhenius definition of acids and bases, and there's also the Bronsted-Lowry definition of acids and bases. So according to Arrhenius, an acid is any chemical that produces hydrogen ions when mixed in water, and bases produce hydroxide ions when mixed in water. So this is pretty much true that most acids and bases follow these rules, but the problem is not all acids and bases, we're not always doing reactions in water. So Bronsted and Lowry came along and gave a more general definition of acids and bases, and this is the one that we more commonly use in chemistry, the Bronsted-Lowry definition. The Arrhenius definition is almost like a shortcut definition, because if it produces hydrogen ions, you know it's an acid. If it produces hydroxide ions in water, you know it's a base. It's sort of a quick way to look at a chemical reaction and decide whether something's an acid or a base. But sometimes, especially if it's not in water, you don't get these 2 products, but you still can have an acid and a base based on these definitions. The Bronsted-Lowry definition is that acids are proton donors, and bases are proton acceptors. By proton, we're really talking about a hydrogen ion. That is a proton. And I have this little diagram for you here of a hydrogen atom. What is a hydrogen atom? It is one proton and one electron. And what if that proton, that hydrogen atom loses an electron and becomes a hydrogen ion, H+, what is left? Just that proton. So when we're talking about protons, we're talking about, or free protons, we're talking about hydrogen ions. Same thing, they're synonymous. So hydrogen ion equals a proton, okay, because that's all it is. So here's an example of an acid, hydrochloric acid, HCl, which dissociates in water into hydrogen ions, or protons, and chloride ions. That's what happens to acids, basically dissociate. So this would be an acid, according to Arrhenius, because it produces hydrogen ions in water. And it would be an acid, according to Bronsted-Lowry, because acids are proton donors. It's donating a proton. You see, it's losing a proton, so it's donating it. So in water, technically, you don't have free hydrogen ions, free protons. Those protons actually will bind to other water molecules to form what's called a hydronium ion. So aqueous solutions don't truly have free protons. What really they have is hydronium ion. So essentially this water molecule picks up that free proton, and now it has 3 hydrogens, and we call that hydronium ion. So these are some words, some terms that you're going to need to know. Make sure you can keep straight. Hydrogen ion, hydroxide ion, and hydronium ion. They all kind of sound the same, but you need to be able to remember which is which. So an example of a base here is sodium hydroxide, which when mixed in water dissociates into sodium ion and hydroxide ion. Okay? So when you are doing acid-base chemistry in water in an aqueous solution, there's always both an acid and a base, because water actually has acidic and basic properties. It can act as either a proton donor or a proton acceptor, depending on what is added to the water. So water has this somewhat unique ability to do this. There's a few other ions that can act as both an acid or a base, but water is very versatile in that way. So for example, here, sorry my slide there's some weird text overlap here, but the HCl here, the hydrochloric acid here, is mixed with water to form hydronium ion and chloride ion. So the hydrogen, the HCl, the hydrochloric acid, loses this hydrogen that's then going to be donated to the water, who accepts it. That's how you get the hydronium and the chloride on the product side. So therefore the HCl is the proton donor, all right, also known as the acid, and the water acts as the proton acceptor, also known as the base, okay? And so now we have an acidic solution because we have a lot of hydronium ion. In the next example, we're looking at how water can act as an acid, because in this example, you have ammonia plus water becomes ammonium ion plus hydroxide ion. So hydroxide ion is produced. So that gives us a clue that it's a basic solution, according to Arrhenius. But if we're looking at who's the proton donor and who's the proton acceptor, the ammonia goes from having 3 hydrogens to having 4 hydrogens. So it's the proton acceptor, whereas the water goes from having 2 hydrogens to 1 hydrogen. So the water is donating a proton to the ammonia. So it is the acid now, whereas the ammonia is the base. Okay? So we're going to practice writing out some equations in each of the following equations, identify the reactant that is an acid, a proton donor, and the reactant that is a base, a proton acceptor. So we don't have little cartoon diagrams. We have to identify it from the chemical formulas, which one is donating and which one is accepting. So in this first one, part A, we have hydrobromic acid, HBr, plus water goes to hydronium and bromide ion. So is the hydrogen bromide, is it losing a proton or accepting a proton? It is donating a proton, okay? This proton gets donated to the water to make it into H3O plus and leave that as Br minus, okay? So then if this is a proton donor, that means it's an acid. If this is a proton acceptor, that means it's a base, okay? Now let's do the second one. Water plus cyanide, I think is this ion, goes to HCN plus hydroxide ion, okay? So let's start with water. Water goes from H2O to OH, so it loses a hydrogen. So one of these hydrogens is getting donated because CN goes to HCN. All right, so our proton donor is which, the acid or the base? The acid. And then that means that this one is the base. The proton acceptor is the base, okay? So again, this problem also goes to highlight how water can sometimes act as a base and sometimes act as an acid, depending on what you're mixing in it, okay? So hopefully that's clear, identifying an acid versus a base, so using the Bronsted-Lowry definition, identifying which reactant is the proton donor and which reactant is the proton acceptor. It's that easy. So when it comes to acids and bases, they come in different flavors, different strengths, okay? Similar to electrolytes. When we talked in the last chapter, we talked when talking about solutions and solubility, that there are strong electrolytes and there are weak electrolytes. Similarly, we have strong acids and strong bases, and that prefix, that word strong, has the same definition for both. So essentially, a strong electrolyte, if you remember, completely dissociates in water when you mix it in water. Same thing with a strong acid or a strong base. They completely dissociate, meaning that this arrow here is one way, and that all of the, when you mix hydrochloric acid in water, all of that HCl becomes H plus or hydronium and chloride ions. There are no HCl molecules actually left. They're all completely broken up and dissociated. Same thing with strong bases. Now there's very few strong acids and strong bases in nature. There's about 6 strong acids, I think maybe about 4 strong bases, and most of the acids and bases in nature fit in this category. They are weak acids or weak bases. Do I have a table? I don't have a table in the lecture, but I think there's a table in your book that lists the different strong acids. There's like 6 different strong acids. And you might want to like tab that page because it'll be useful for some of the problems, some of the homework problems, referring to that table. And I will not require you to memorize strong acids, the strong acids for this class. I will provide them for you on the test if it's relevant. Or I will provide you the information whether something is a strong acid or a weak acid. Okay? But generally, acids and bases in nature are weak acids, meaning that they do not fully dissociate. They only partially dissociate. Hence, the double arrow here, the equilibrium arrow showing you that some of these, so this is a acetic acid, don't really need to restore the writing. Acetic acid, which is vinegar, acetate, becomes acetate. It loses a proton, so it becomes acetate and proton. Or in water, technically, it would become acetate and hydronium ion. Okay? But not all of the acetic acid is going to dissociate. Probably less than 5%. It's really only a small amount that will actually dissociate. Similar, and you'll notice this is the same molecule we used as an example when we were talking about weak electrolytes. Weak acids are weak electrolytes because they have that carboxylic acid group. Weak acid, carboxylic acid, okay? And that weak dissociation gives them a weak electrolyte capability, but also gives them a weak base title. Okay? So when you take an acid and a base and you mix them together, we call this a neutralization reaction. Okay? So I'm going to sort of walk you through the derivation of a neutralization reaction right now. So mixing an acid in water, HCl plus water, becomes hydronium ion and chloride ion. Take a base and mix that in water, all right, sodium hydroxide in water, becomes hydroxide ions and sodium ions. Okay, now if you add these two reactions together, you get two waters and sodium chloride, a salt. All right, and we're going to see on the next slide that that's the basic formula for an acid, for a neutralization reaction. If you mix an acid with a base, what you end up with as a product is water and sodium, or water and a salt. In this case, it's sodium chloride. So something else to know, a little sort of brief introduction into thermodynamics here a little bit, is that when hydronium ions and hydroxide ions react to form water, like in this reaction here, okay? When you add these two reactions together, when hydronium reacts with hydroxide to form two waters, it also releases heat. If a reaction releases heat or produces heat, it's called an exothermic reaction. You can actually feel this. If you mixed these two together, and if you mix hydrochloric acid and sodium hydroxide together in a beaker, you'll actually feel the beaker warm up because of this exothermic reaction here. It produces heat. It releases it so it feels warm to your hand. Okay, so this reaction, it releases heat. In other words, it's exothermic. So like I said, mixing an acid and a base together is referred to as a neutralization reaction. And it's when you mix an acid and a base and you get a salt and water. Okay? And also just wanted to point out on this slide that this is a balanced equation. Notice that the number of hydrogens on each side is the same. So there's 2 hydrogens in the reactant side. There's 2 hydrogens in the product side. 1 sodium, 1 sodium, 1 chloride, 1 chloride, 1 oxygen, 1 oxygen. We are balanced. We have a balanced equation. All right? So let's practice writing some neutralization reactions here, okay? Some where we're mixing an acid and a base. So in this problem, HNO3, this is nitric acid, it's a strong acid, mixed with potassium hydroxide, which is a strong base. Okay? So our product is going to be salt and water. So I'm going to go ahead and write the water first, probably in liquid, and then our salt. So I like to, let me just go back and say this one more time. So my analogy for doing these equations, for solving, these equations, figuring out what the product is going to be, is think of it like each of these are ionic compounds, right? You have HCl and you have NaOH, okay? So these are like a husband-wife pairs, okay? They're married couples. After you go through the reaction, you think of them like swingers. They switch partners, okay? So hydrogen, instead of bonding with chlorine, is now going to bond with hydroxide to make water, and chlorine and sodium are going to bind together to make sodium chloride. That's how you get your reactants or your products. So we can do the same thing here, okay? So we have, you can write it out if it makes it easier for you. Okay, I'm going to write it out here. Okay, so our partner switching, so we have hydrogen now bonding with hydroxide to make water. And now we're going to have our salt is going to be potassium nitrate. Remember, the cation always comes first. So potassium nitrate. Do we have the same, is this a balanced equation? Do we have the same number of molecules on each side? Let's check. How many hydrogens do we have? 2 and 2. How many oxygens do we have? 4 and 4. How many nitrogens? 1 and 1. Potassium, 1 and 1. We're good. All right, so that one's balanced. Let's do this one now. I'm going to do my little 2 plus OH minus. Okay, so I can already tell we're going to have to do a little balancing for this one. So first, we'll switch partners. We'll write down what our products are. Our products for this one are going to be water and calcium bromide. Calcium bromide. But can we write it like this? Is this calcium bromide? Is that a correct answer? No, because calcium has a 2 plus charge and bromide has a 1 minus charge. So we have to have those charges cancel out when we make an ionic compound. 1 calcium ion is going to bond with 2 bromide ions. So our proper chemical formula is going to be calcium bromide, CaBr2, right? We do that cross multiply. So now we've got to check and see that we're balanced, which I'm already going to tell you we're not. So we have 2 hydrogens here and 2 hydrogens here. Check, that's okay. We have 1 oxygen here and 1 oxygen here. So that's okay. We're probably not going to, we don't need to change our coefficient on our water molecule. We have 1 calcium and 1 calcium. Cool. And we have 1 bromine and 2 bromines, so that's going to be a problem. We need to multiply this one by 2 because we need to have 2 bromines on this side. But you know what? I should recant my last statement about the water because look what? If we did 2 bromines here, now we have 2 hydrogens plus 2 hydrogens here is 4 hydrogens. So now we're going to have to double the number of waters we have, so we have 4 hydrogens on both sides. Oh, I counted wrong before. That's my bad. I counted, when I was counting originally, we were not balanced on hydrogens and oxygens. So, because I was counting off my ion, but I didn't account for the fact that there are 2 hydroxide ions. So, when you're doing this shortcut, remember to ignore it when you're balancing, okay? So let's rebalance this one based on what's actually written in the equation, all right? We have 2 hydrogens plus 2 hydrogens makes 4 hydrogens. 2 times 2 is 4 hydrogens, so check. Bromine, we have 2 bromines here and 2 bromines on that side, check. Calcium, we have 1 calcium here, 1 calcium here, check. And I think the last one was oxygen. We have 2 oxygens here and we have 2 oxygens here, okay? So we are balanced in the clear. So balancing equations is really, it's really sort of a trial and error kind of a thing. There's no real shortcut to it. You just kind of have to go through each compound and ask, are they balanced on each side? If not, you alter, you add a coefficient, and then you do it, recount it again. And with practice, with time, doing lots of different problems, you just get the hang of it and you get faster at it. And that's balancing an acid-base reaction. So weak acids, like I said, most acids and bases in nature are weak acids or weak bases, and antacids are actually weak bases that we use to neutralize stomach acid. So has anyone ever had heartburn? I know I have, not until I was pregnant, but it was not a pleasant experience. It's sort of like a burning sensation. People get at different spots along the esophagus. And it's very uncomfortable, and essentially it's caused by stomach acid from the stomach leaking back up into the esophagus and literally burning it, causing an acid burn. The acid in your stomach is very acidic. It's very strong. And so taking antacids like Tums or Mylanta or Malox or whatever, a whole bunch of different brand names here, are ways, they're basically weak acids that help to neutralize the acid so that it's not burning you anymore. And there's a whole bunch of different chemical formulas for each of these antacids. So the different brands are different chemical compounds. So Tums, your typical Tums tablet, is made of calcium carbonate, which is why a lot of people will actually take Tums as a calcium supplement. Tums contains a lot of calcium, so some people actually will just take it as a form of a calcium supplement. It's also why it's not good to take too many Tums, because getting too much calcium, having too high calcium in your blood can be bad for you. It also produces carbon dioxide. Weak acids, weak carbonic acids, when they're neutralized, they produce water, salt, and carbon dioxide. So it often makes you feel like you have to burp. After you take Tums, you often get this burping sensation because it actually produces a little bit of gas in your stomach. Some of these other ones have hydroxide bases, so like a metal hydroxide, aluminum hydroxide, magnesium hydroxide. Magnesium hydroxide actually has a laxative effect as well, so it actually promotes movement of the bowels. And Alka-Seltzer is, so all of these different, I guess what I'm trying to explain here is that all of these different antacids, they will all work the same to neutralize stomach acid, but each of the weak bases has additional side effects, can have additional side effects that affect your health, that might affect your choice of which laxative to use, which antacid to use, because they all have similar abilities to actually neutralize the acid. So this last one here, Alka-Seltzer, is sodium bicarbonate, which is essentially baking soda. So, which is fine. There's nothing wrong with that, with Alka-Seltzer, except that it does contain sodium. And for people with hypertension particularly, or people who eat a lot of sodium in their diet, or who are just trying to cut down on their sodium, would want to avoid Alka-Seltzer because it does elevate your blood levels of sodium, which can be an issue. So all things to kind of think about if you do get heartburn and you use one of these antacids. You might consider your choice and maybe even reconsider your choice based on some of this information. Knowing that they all work the same. They're all weak acids or weak bases that neutralize acid. So I sort of mentioned this with the weak acids and weak bases before, that they have this equilibrium arrow, right? Because they don't fully dissociate. They only partially dissociate. They're actually at equilibrium with each other, the products, the reactants, and the products. Meaning that the reactants are reacting to form products, but the products are also reacting to form these reactants again, okay? So the reaction is going both ways. At equilibrium, what's happening is that the forward reaction and the reverse reaction are occurring at the same rate, okay? This is important. They're occurring at the same rate. So it doesn't mean, at equilibrium, it doesn't mean that you have the same amount of reactants as you do products, because you don't. Remember we said weak acids only dissociate about 5%. So at equilibrium, the products will be about 5% of the amount of the reactants, okay? But what equilibrium means is that the rate that is going to the right is the same as the rate that is going to the left. And I have this nifty little analogy in a minute. So this slide has an animation on it that kind of explains it, okay? So in a chemical reaction, reactants start going to products, okay? In a reversible reaction, the products also can go back to the reactants. And at equilibrium, the rates of going forward and going backward are the same, okay? And as you can see here, I've purposely made the reactants bigger than the products, so you can see that at equilibrium, it's not necessarily the same amount of each. It's just the rate of this reaction is the same as the rate of this reaction, of the reverse reaction. Most reactions in chemistry are reversible, they do achieve some equilibrium. Again, most acids and bases in chemistry are weak acids and bases and they are reversible, meaning that they can go forward to become products, but the products can also sort of back react to become the reactants again. So memorize this definition. Chemical equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. Okay? So here's my nifty analogy that the book uses that I like. I think the book uses this one. That tells you a little bit about equilibrium. Maybe the book uses the concert one. I can't remember. So let's say you have a ski mountain, okay? And you have a ski lift. You're at Whiteface. You're going up a ski lift, okay? And let's say that at any given time, there's an average of about 20 people at the top of the mountain, okay? And at the bottom of the mountain, there's a big long line waiting for the ski lift. So you have, like, let's say 200 people on average at the bottom of the mountain at any time, okay? So the ski lift moves at one speed. It carries people up at the same rate that it carries them down. So this would be at equilibrium. This system would be at equilibrium. The rate of people going up the mountain is equal to the rate of people going down the mountain, because the ski lift goes up the same speed that it goes down, okay? It doesn't mean that there's the same number of people at the top of the mountain as there are at the bottom of the mountain, right? But it does mean that there's the number of people at the top isn't really changing. There's always about 20 people at the top of the mountain. It's not the same 20 people. You drop some people off and some people go down while you drop some more people off. So there's always about 20 people, but there's, it's changing. Those 20 people are changing. Same thing at the bottom. There's always about 200 people there, but the people are different people. People are changing. So this is just like a chemical reaction. It's a dynamic system. It's always moving. But if you just took a snapshot of it, it looks like there's 20 people at the top and 200 people at the bottom, and it's not changing. When really, technically, the reaction is still going, still taking people up, still taking people down. All right, and go back to the chemical reaction analogy. The reaction's still going in the forward direction and still going in the reverse direction. You're still making more product, but you're also still making more reactant through the reverse reaction. So it looks like the amounts are not changing. They look like they're staying constant, but really they're just, it's just in flux. This is similar to insolubility when I had that slide where I showed you like a cube of salt that in a saturated solution where it's going into solution and crystallizing at the same rate. So at equilibrium, the rate that it goes into solution and the rate that it recrystallizes is the same. Okay, equilibrium are all about the rates being the same, and so they're being changes that you can't really detect because the rates are the same. So even though these 20 people are changing, it looks like there's always 20 people up there. So it looks like a constant. Hopefully that makes sense. Let me know if it doesn't. So when we're talking about equilibrium reactions reversible reactions that have an equilibrium arrow, all right, that reach equilibrium, each reaction that is reversible has what is called an equilibrium constant. This is a ratio of products to reactants that basically always happens. No matter how much product or product you start with, you're always going to end up with a certain amount of product based on the equilibrium constant. So it's a mathematical formula, and it may look a little tricky, but it's actually very simple. The basic formula for the equilibrium constant, K, what we call it, is the concentration of the products divided by the concentration of the reactants. That's the basics of it, okay? So let's take that reaction we had before of nitrogen plus hydrogen gas reacting to form ammonium, okay? The equilibrium constant for this would be the concentration of the product, which is ammonium, okay, on the top, divided by the concentration of each of the reactants, the concentration of nitrogen and the concentration of hydrogen. Now, first thing I should point out is that these brackets, when you have brackets in chemistry, that's like an international symbol for concentration. Brackets mean that the units we're looking for are concentration units. The other thing to point out here is these little superscript numbers. Where did those come from? Where did they come from? Let's look at the reaction. Hopefully the gears are turning and you figured out that those superscripts have come from the coefficients in front of each of those chemicals, okay? So we take the concentration of, technically the formula is the concentration of the products over the concentration of the reactants to the power of their coefficient. So for example, if there's the coefficient for ammonium here is 2, so it's the concentration of ammonium squared, okay? And I have that again on this slide a little bit more clearly. So if you have a reaction, and the basic formula for that reaction is a reactant A plus reactant B becomes product C plus product D, with the little letter being the coefficient, the number. All right, then your equilibrium constant would be products C and D raised to the power of their coefficients over the concentration of the reactants raised to the power of their coefficients, okay? Now, the only other sort of tip or rule, the only other rule when determining equilibrium constant, K, is that only gases and aqueous products and reactants are count. They're the only ones that count. Liquids and solids do not count. They do not, and the reason is because pure liquids like water, and solids don't have a concentration. What's the concentration of water? It doesn't have a solute in it, so it doesn't have a concentration. What's the concentration of sugar? It's not a solution, understand? Okay? So it can't change its concentration. It can't change the amount per volume. Gases and aqueous solutions can change concentrations, so they can go into this equation. So we'll have a couple of problems where I demonstrate that. So you do, when you're figuring out equilibrium constants, you do actually need to take note of what the state is of the reactants and products. Okay? So here's some examples. We're going to write the basic formula for the equilibrium constant K for each of these reactions. Okay? So remember, and I mean, it's helpful just to write out the definition. All right, on a test, I would give you partial credit just for writing this, even if you didn't know how to plug it in. All right, this is half the battle, is knowing that K, the equilibrium constant, this shows me that you know what I'm asking for. I'm asking for the equilibrium constant, and the equilibrium constant is the concentration of the products over the concentration of the reactants. In this problem, what are the products? Carbon monoxide, CO. So concentration of CO. Is there a coefficient? No, so we don't need to write anything up there. Always the power of 1 is, you don't need to write it. And the other product is hydrogen gas, H2. All right, but it does have a coefficient of 3, so we raise this to the third power. All right, and I should have mentioned, but I was checking this, but I should have reminded you to check that each of these are gases, so they're kosher to go into the equilibrium equation. Same thing here. Now let's look at our reactants. Let's first check, are they gases or aqueous? Yes, they are. So they both need to go into our expression here. So CH4, no coefficient, so no power, and H2O. All right. H2O, and I should point out, I just made the point that water doesn't have a concentration, okay? Water liquid doesn't have a concentration, but water gas, any gas can be compressed, and its concentration can be changed because it can be compressed. So because it's gaseous water, it does go into the equilibrium constant equation, okay? So just remember, if it's gas or aqueous, bam, it goes into the equation. So that's it. That's our K. That is the equilibrium constant. This is how we would calculate the equilibrium constant for this the first chemical reaction, okay? How about this chemical reaction? Again, K equals products over reactants. So what are our products? These are the products on the right side. We have one gas and we have one solid. Solids do not go into the equilibrium expression. So K equals the concentration of CO2. All right. And now for our reactants, do we have any reactants that we can put into the equation? We don't. Our reactant is a solid, so it's not going to go into the equilibrium expression. So our equilibrium constant for this reaction is just the concentration of carbon dioxide. The equilibrium is only affected by the concentration of carbon dioxide. So now we're going to end up doing some problems where we're actually going to start plugging in numbers. We're actually going to talk about what the value of the equilibrium constant means, okay? So that's just sort of like equilibrium constant theory a little bit. So what does this mean? The equilibrium constant is the ratio of the products to the reactants, okay? So you have a reaction. Let's say reactants, and here's your equilibrium arrow, to products, all right? If you have more product than you do reactant, okay, then this top number is going to be larger than this bottom number. Therefore, K is going to be greater than 1. Thus, if you have a K of greater than 1, it means that the reaction favors the products, that you end up with more, that at equilibrium, you have more products than you do reactants, okay? Vice versa, if you have a lot of reactants at equilibrium, the reaction favors the reactant side. You have more reactant left. Oops. then your K value is going to be less than 1. So a K value of less than 1 means that you favor the reactants. So that's the thinking process. I'm walking you through how to solve this. You can also just commit this little table to memory. K of greater than 1 favors products, K of less than 1 favors reactants. But I personally like to understand why that is, because then I don't have to remember it. I can figure it out. I can always figure it out, so that if I'm stressed out on a test and I can't remember, I'm confused, oh my god, which one was it? Was K greater than product? If K is greater than 1, does that mean it favors products or it favors reactants? I can't remember, I'm confused. I just think about this reaction, and I think if products, if K is greater than 1, that means that this number has to be higher. The number on top has to be higher, so it has to favor products, okay? And then, obviously, if K is equal to 1, it means that the numbers here and here are equal, that the amount of product is equal to the amount of reactant. That's fairly rare. It's fairly rare that a reaction, an equilibrium reaction, actually does have equal amount of reactant and equal amount of product at equilibrium. But it can happen. Okay? So now we're going to do a problem where we actually have the concentrations of the reactants, or sorry, no, we're still not doing that yet. Based on the value for K, okay, so now we're just practicing that concept. Based on the value of K, we want to know whether this reaction favors the products or the reactants. So the K for the following reaction is 25 at 25 degrees Celsius is 1 times 10 to the 2, which is also just 100. Okay? So the K is 100. And this is the reaction. Carbon monoxide plus water becomes hydrogen gas and carbon dioxide. So based on the value for K at equilibrium, are the products, based on the value for K at equilibrium, are the products or reactants greater? So you don't actually have to do any math necessarily or set up an equilibrium problem. If you can remember from that table that whether, if you remember that table, if you have it memorized. But let's just set it up very basically, okay? I just want to write this out. Just to walk through the thinking exercise, okay? If this K is equal to 100, or 1 times 10 squared, then does that mean that the products are higher or that the reactants are higher? The products are going to be greater than the reactants because this is greater than 1. 100 is greater than 1. So therefore, it's the products that are favored. The products are greater at equilibrium. That would be the answer, okay, for this problem. So I guess I take it back. I guess we don't do any actual math problems. You don't actually have to calculate any equilibrium constants for the class. You just have to be able to set up the equation. I have to go through the homework problems and double check that because I can't remember, and I don't have the book in front of me right now, so I apologize. But another really cool thing when it comes to equilibria is that you can shift the equilibrium. You can manipulate it, and that is actually really cool and really handy in industry, okay? And this concept of being able to shift the equilibrium was first discovered and described by, I think, a French chemist named Le Chatelier. And so this is called the Le Chatelier principle. But let me just give you an example from another chemistry book that I have. That let's say you are trying to start a business, a chemistry business. And one of the most lucrative industries in chemistry is the production of sulfuric acid. Sulfuric acid is used in car batteries. It's used in fertilizer production. It's used in, like, I don't even know all the different uses for it, but apparently it is the most used chemical on the planet. Sulfuric acid, who knew? So sulfuric acid production is actually a really lucrative industry. So let's say you want to start a home chemistry lab and produce sulfuric acid and sell it or something. So you set up the reaction to produce sulfuric acid, but it is a reversible reaction. It doesn't go all the way. So your product that you want, sulfuric acid, you're only getting 80% of the reaction is going to products. And you want 100% of it to go to products. You want to make more of it go to products so that you can get more sulfuric acid so you can have more efficient production. Well, Le Chatelier's principle comes into play here, and this is something that's used a lot in industry to increase production, particularly even just go back to that, our example equation that we keep using of producing ammonium, okay, from hydrogen and nitrogen gas. All right, this reaction does not go to completion. It's reversible. So you're only going to make some ammonium from these reactants. But what if you want to make more ammonium? So Le Chatelier's principle tells us how to do that. And just kind of also, this is what happens in your body as well, physiologically, when when you have an equilibrium. So your body essentially is always striving to achieve homeostasis. It's striving to achieve a state of sort of constant, like baseline in terms of pH of your blood, in terms of your blood glucose levels, all different chemicals in your body. There's like an optimum, concentration for them, and your body tries to keep it that way. And that's at an equilibrium state. If you shift that equilibrium by, I don't know, there's some different examples we'll talk about how you can, or like in chapter, or did we talk about acidification of the blood? No, I guess we talk about it in this chapter. If the blood becomes acidified from like hyperventilating, then you can get respiratory acidosis, and it can cause the shift in the equilibrium of the blood, the acid-base equilibrium of the blood. And through Le Chatelier's principle, we can reshift it back, okay, and reestablish our equilibrium. So, what is Le Chatelier's principle? I like this analogy here. So let's say you have a reaction and it's at equilibrium, okay? So, and this is kind of a bad example because in here I have the reactants and products. They're balancing, so that means that they're the same amount. But just keep in mind that at equilibrium, the amount of products and reactants are not necessarily the same amount, okay? So but let's just say you have a reaction and it's at equilibrium, okay? And then what happens? You add more product. A reaction occurs in some kind of vessel, and you add more product now to that vessel. So now you've tipped the equilibrium. You've tipped the scales. So what's going to happen? That reaction wants to get back to equilibrium. That is its goal. So what does it need to do? It needs to shift back in the other direction. You need to take some of that product and make it back into reactant, to get back to equilibrium, okay? And that's what happens with Le Chatelier's principle. If you stress the system by adding or subtracting more product or more reactant, you're going to cause the reaction to shift, okay? So this is, I really like this figure from the book because it explains all the sort of possible scenarios. And using our ammonium example, okay? So if you add something, if you add a substance, either one of the reactants or one of the products, it's going to cause the reaction to shift in the other direction, All right, think about the scales. If you add a product, if you add a product to this side, all right, the scales tip. So you need to tip them back. You need to move the reaction in the other direction in order to get the scales even again. Now, if you remove a product, or in this case, if you remove a reactant, or if you remove a product, if you remove a substance, the reaction is going to shift in that direction, okay? Let's try this again. So let's say I remove some product, okay, this is my product hand. If I remove some product from a scale, then the reaction's scale is gonna tip like this, right? Because now it's lighter on this side. So the reaction needs to shift this way. We removed something from this side, the scale's tipped, so now the reaction needs to move this way to get them balanced again, okay? I don't know, this scale analogy works for me. That's how I think of it. But if you can memorize this diagram, you can also think of it that way, or these sort of statements. Anytime you add a substance, the reaction is going to move in the opposite direction. Anytime you remove a substance, the reaction will move to that direction, to that side to replace it. Okay? Oh, I don't have examples yet. Another thing that affects the reaction equilibrium is temperature, and there's another stressor you can put on a reaction. So I mentioned earlier that about an exothermic reaction is one that releases heat, okay? And an endothermic reaction is endothermic reaction absorbs heat. So another way to sort of indicate exothermic, endothermic reactions is to write heat either as a reactant or a product. So in an exothermic reaction, it produces heat. All right, I have this as a question for you here, but I'm gonna just give you the answer. Okay, an exothermic reaction, since it produces heat, heat is a product. Okay, it produces heat. So heat is a product. So this would be an exothermic reaction. We could write heat actually in the products area as a product. An endothermic reaction uses heat. It absorbs it. So heat is like one of the reactants. So then in an endothermic reaction, you would write heat on the reactant side. Okay? And that makes a difference, because then if you take an exothermic reaction and you add heat to it, all right, that's stressor. It's like adding product, all right? So if you add heat, which way is the reaction going to go? If you add heat, the reaction to this reaction, since heat is a product, if you add heat, it's going to move, it's going to shift to the left, okay? But if heat was a reactant and you added heat, it would shift to the right. Does that make sense? We're going to work some examples. So, this is what I was just saying. When heat is viewed as a product, such as in an exothermic reaction, then it just becomes like another product, and it follows the same principles, the same Le Chatelier principles, that adding it will cause it to shift in the opposite direction. If you cool the reaction, if you remove heat, so you cool the reaction, it's going to move towards the product side. Okay? And then here's sort of a little table that gives you sort of the basic rules to Le Chatelier's principle in a table format. I'm more visual, so I like that these arrows, I like this kind of a format myself, but some people like to see things more concise. So either way. So here's some practice problems. How does each of the following actions affect the equilibrium of the following reaction? In other words, does it shift it right or does it shift it left? Okay? So if we add oxygen gas, whereas oxygen is a reactant, so if we add oxygen, we're going to tip the scales towards the reactants. So we need it to go in the other directions. If we add oxygen, it's going to shift to the right. Shift right. Okay? How about B? What if we lower the temperature? If we lower the temperature, give you a minute to think this one out. Okay? If we lower the temperature, it's like heat is a product. This is an exothermic reaction. Heat is a product, so if we lower the temperature, it's like we're removing product. Therefore, the reaction is going to shift in that direction towards the product, to the right. And the last one, if we add SO3, we add sulfate, I think it is, all right, which is a product. So if we add more product, which way is it going to shift? Hopefully you got it. It shifts to back this way. If you add more on one side, it's going to shift to the other side, okay, to try to balance it out. So keep practicing these problems. It's just a set of rules. It's a set of rules that you learn them and practice them, and they will make sense, and they will be pretty straightforward. Okay? So these principles of equilibrium apply to weak acids and weak bases because they are at equilibrium, right? They only partially dissociate. So here's a quick question for you, pop quiz. What would be the equilibrium constant expression for this reaction? Go ahead and write it out. See if you remember. We've been talking about Le Chatelier's principle for a few minutes now, but do you remember when I say the equilibrium constant, what am I talking about? What is the equilibrium constant? It's K. Okay? K. And K equals what? Go ahead and tell me. Concentration of the products over the concentration of the reactants. Okay? So, go ahead and write out what the equilibrium constant for this reaction would be. I don't really like having long pauses in these videos, so I encourage you to pause the video right now while I write the answer up here for you. But I encourage you to pause it and come back and see if you got it right.